So I want to take one final lesson and do a few more practical applications of trigonometry. So in the last lesson, we looked primarily at surveying or excavating type scenarios, that figuring out slopes, those kinds of things that you would need to know trig for. In this lesson, I want to look at some buildings, stair railings, building rafters, and I'll do one gazebo question just for the sake of, I said they exist that way, and it's actually a pretty easy question once you've seen it done. It's not too complicated. I always used to do it with the cabinet making crew because octagons and hexagons are something that they needed to know how to calculate all the pieces of, but it fits nicely into carpentry as well. So this is actually a picture of the staircase in my home. So I snapped a few pictures while we were, and so what I want to figure out is what's the angle of incline of the stairs. So there's 13 stairs. They have a rise of 7 inches. It's supposed to be an inch. I got a typo in there. And a run of 11 inches. And I want to know what's the angle of incline. And I want you to think about why would it be essential to know that particular angle. And perhaps if you're not sure now, the next slide will make it even more clear why you need to know that. So the angle of incline of the stairs. So there's a little trick with stairs. If each step is a rise of 7 inches and a run of 11 inches, if we were to make a triangle using just one step, okay, just one step, if I was to make a triangle just using that, it should be the same as the angle I get at the base of the stairs, okay? So we don't actually have to worry about the fact that there are 13 stairs in this scenario, simply because we're looking for the angle. In some cases, we might have to worry about the 13 steps, but in this situation, we don't have to. That's the nice thing about triangles is if the angle stays this, if the ratio of the sides stay the same, the angle will remain the same. And that's the whole principle behind sine, cosine, and tangent. So to find the angle of incline for the stairs, I'm looking at, okay, what's this particular angle here? I know that it has a run of 11 inches and a rise of 7 inches. Now we need to figure out, well, what ratio will we use to solve that? In terms of our sides, this is my hypotenuse. This is our opposite. This is our adjacent. So we're going to use tan. So the tan of the angle of incline is going to be opposite, which is 7 inches, over adjacent, which is 11 inches. Then we have to do our rearranging. And we do that shift tan because we're looking for the angle. Is equal to, oops, shift tan. I've got an extra number in here. Just one sec. Extra equal sign. So our angle will be equal to, we'll do that shift tan, and then we'll put our ratio in. 7 over 11. And you may have calculated that as a decimal first. If you calculated it as a decimal, please make sure you keep 4 decimal places before you hit that shift tan. And you will find your angle is equal to 32.5, or that would round to 33 degrees. So that gives us our answer for A. So why do we need to know this angle? Well, at the base of my stairs here, I have a cut. That wood trim has to line up. I can't use filler in order to fill in and make it look good. So we need to know what angle to set our miter saw here. If I had it drawn higher, you've got another angle here at the bottom of the stairs. That's going to be related to our angle of incline. So we would need to know what is that angle. Also, each of the balusters, they all need cut to the 33-degree angle in order to line up into the railing. I'm going to look at one example of what happens when you have, you'll see here, I have 2 rungs that sit on the same step. But those 2 are different heights. You can tell they're different heights because if we just look at this kind of fancy trim piece here, it's up almost level with this step, but this one is down much lower. In order to figure out that height difference, which we will calculate in a future slide, we need to know what is our angle of incline for the stairs. So stairs have lots of applications where you would use angles, although you'll use the tan ratio for them more than you would use sine or cosine. Now, in my particular home, we have a good angle challenge. This whole stairway is oak wainscoting, and then there's this lovely trim that goes around. There's a balcony up here, and this trim goes around using, I think, sewing terms, so I was going to say the seam, the floor joists between the first floor and the second floor. So that's where this trim happens to sit. And it actually continues all the way around in the whole entryway. But I decided, well, let's take one section of this and let's see how we would apply our angles to it. So these are the same stairs as in the previous question. And I want to know, what are the angles that I would need to figure on this particular piece in order to be able to cut it out? And not only cut it out, but we also have to be able to do the miters in order to fit everything together. We know how to do one piece. We could figure out any of these other ones. So I'll just take this one for now. Well, the first thing we'd need to know is our angle of incline. So if you remember, they're the same stairs. So the angle of incline was 33 degrees. Okay, so we'll just keep that in mind. We don't have to recalculate that. You could. If this is my piece of trim and it connects to this, so kind of like a railing, this molding, but the angle on this molding matches the angle on my stairs. So if this is like a step with a rise of 7 and a run of 11, that ratio, then this angle here will always be 33 degrees. And that's going to let us calculate some of the other angles. Okay? So if I take 33 degrees and I add it to angle B, what would the sum be? Well, 33 degrees plus B would be 180 because it's going to make a straight line. So if I want to know angle B, it's going to be equal to 180 degrees minus our 33 degrees, minus our angle of incline. And 180 minus 33, 180 minus 33 leaves me with 147. Pretty easy calculation, but we had to know what the angle of incline was first in order to figure out what would that angle be. Now, if I was actually cutting this trim, what we do is we actually, in order to make it look good, you split that angle, and instead of using 147 degrees and butting them up, I shouldn't say up here, you can kind of see where this one's butt normal, but you can see there's the miter on the trim, and then there's another miter here. What they do is they take the angle and they split it in two. So each piece takes half of that angle. Lets the trim fit together really nicely and gives it trim work has to look pretty. This is where carpenters have to think about what makes it look pretty. And in this particular scenario, you have to work at being really accurate because you can't worry about, you don't have the opportunity to really use much for filler. Now let's look at angle A. So if this is like our steps with rise of 7 and a run of 11, then we could look at, well, let's look on this side. If I put a line straight up, this would be 7 and here would be 11. So the angle A has to match my angle of incline. So this would actually be 33 degrees. Can you see how that would be? So if it's 7 on this side, it would have to be 7 on that side. It's 11 on the bottom, it has to be 11 on the top. And that's just our side ratio. That might not be the actual measurement of these two pieces, and I didn't even measure them. I just looked at one step. But the ratio, the rise-run ratio here, will have to match the rise-run ratio of the stairs, which was a run of 11 and a rise of 7. centimeter. Go back here. There we go. Rise of 11 and a run of 7. Okay, so angle A is equal to our angle of incline, which is 33 degrees. This question, we really didn't have to use any extra SOHCAHTOA. We just had to think about how was what we calculated before related or connected to what we had just got. Does that make sense? So all we're doing is we're taking the angle that we calculated before, and we looked at it and said, well, if this is 7 and this was 11, if the ratio of the sides on this side of the rectangle would be the same, then the angle would have to be the same as well. If you're not 100% sure about that, send me a message, let me know. I miss the questions that sometimes we get in class that allow me to clarify or make something more clear, pick up a misconception. All right. If you could also calculate what angle A was, and if you wanted to find B, if you knew what the angle of this part of B was, you could add 90 degrees to it. So there's a couple ways you could calculate this question. You have a different way to calculate it. All right, this is a great question, and it's a lot like the steps that I have in my house. We can ignore the 13 stairs. So let's just take that out. I'm not going to re-record this just for the sake of time. I've had too much re-recording the last couple of days due to files that didn't save and then vanished. So these stairs have a rise of 7 and a run of 11, and a run of 12. Okay, so they go up 7 inches and a run of 12 inches. And I didn't really check to see does it match with the diagram, so I apologize if it doesn't quite match. It looks like it might be out a little bit. Anyway, so here, based on this information, we can find out what the angle would be that we need to cut the tops of these balusters. So in order to find the angle, we look at this little triangle up here and we think, what would the ratio of those sides be? Well, that ratio has to match the stair ratio, which goes up 7 and out 12. So what's the angle? This would be the angle that I need to do my cut at. Well, again, you can see for A, we're going to have to use tan. So the tan of our angle is equal to opposite of 7 over 12. Okay? Then we're going to do our shift tan. So inverse tan of 7 over 12 gives us 30 degrees. So 30-degree angle. So I'm going to have to cut the balusters at 30 degrees. B. If 2 of the balusters, so 2 of these, are 3 inches apart. Okay, there's 3 inches between them. You'll see they have different heights. I want to know what would the difference in height be if they're put 3 inches between them. So it's actually a really easy question. We know what the angle is here. We know that the angle here is 30 degrees. So we can figure out what the height difference is. So we'll just do a little sketch. We know it's a 30-degree angle. And we know there's 3 inches between. And we want to know what's the difference in height. So again, we're using tan. So the tan of 30 is equal to opposite, which is our x, over adjacent, which is 3. And the difference in height is going to be 3 times the tan of 30, which gives me 1.73 inches. And if you wanted to put it into a fraction form, you would get 1 3/4. That's this, even if you follow through to the nearest 16th, it'll round to 1 3/4 inches. So the difference in height that I would have to cut these, I'm going to have to cut this one, See how it's not quite as tall? I would have to cut it 1 3/4 inches shorter than the first one. So just thinking about what's the triangle look like and just breaking apart little pieces. But with stairs, think about with stairs, you don't have to know all of the steps. You just need to know what's the rise and the run of one stair, and that will tell you the angle that works for all of them. All right, now I wanted to jump into another question that has some rafters. 30-degree and 60-degree angles are favorites in pretty well all the trades. So there's a few questions here that use 30s and 60s quite a bit. So in this example, we have a rafter system. And let's imagine you have to build this. And I want to know what's the length of each piece and what's the angle at the peak. So we'll work down through it, and it's much easier. For all that it says it's 5 parts, it's actually really easy 5 parts to calculate. So A says, what's the length of BC? So we want to know what is this length here. Okay, so we know we have a 30-degree angle. We have an adjacent side that's 3 meters, and this particular side would be our opposite side. So we know we're going to use a tan ratio. So the tan of 30 degrees is opposite, so I'm going to call it BC over 3. And length BC is equal to 3 times the tan of 30, which gives us 1.7 meters. Okay, so there's our first piece calculated. B, what's the length of DE? So I want to know, well, how long is this one? You'll notice it shares the same. We could make a large triangle that is 6 meters long, still has 30 degrees, and then we calculate what the height would be. Now there is an easier way to calculate this, and I'll give it to you once we've done it. Equals DE over 6 meters this time. So DE, that is supposed to be a D, is equal to 6 times the tan of 30. 6 times the tan of 30 leaves us with 3.5 meters. Now in this case, you don't quite see it. Let's see how this is 1.7. And then if we double the distance from the angle and have, and all this, we're sharing the same sides, sharing the same angle. Sorry, I feel like I have a sneeze coming. You'll notice the height, BC, is about half of DE, or the height doubles if the distance doubles. And that's something that happens on a regular basis. So if your triangle shares the same side, same angle, and one of the sides doubles, then the other side will also double. So one of those little tips along the way. C. So we've calculated this one, we've calculated this one. So this was 3.5. The 1.7 was to 1.7 because we're rounding, I think it's 1.74. So that's where that 3.5 actually does work out. What is the length BE? So I'm going to know, what is this length here? Well, this is, if you look at it, this is a hypotenuse. We have a 30-degree angle in here, and we have a hypotenuse here. We also have an adjacent side. So the ratio that uses hypotenuse and adjacent is cosine. So the cosine of 30 is equal to adjacent over hypotenuse will give me 3 meters on top divided by the length of BE. BE is going to be equal to, remember these two trade places, that's the shortcut, they trade places, so it's going to end up with 3 over the cosine of 30. Anytime you're looking for something and it's on the bottom of the fraction, it trades places with what's on the top of the fraction, what is on the other side of the equal sign. Right? You can do the long rearranging for it. If you can't remember the long rearranging, take some time to memorize that shortcut. And we get 3.5 meters. Okay, so that's our BE. Okay. And then we want to know, finally, I want to know what's the length of AD, this one. So AD, I know here, oh, let's resketch the triangle. So this is AD. I want to know what's that. That's our hypotenuse. I know we have 6 meters here, and I know we have 30 degrees here. So I'm just resketching the triangle. Might make it a little easier for you to see. So that means it's adjacent, so we're going to use cosine again. So the cosine of 30 is equal to the hypotenuse. So what's on the bottom, that's our AD. So the point between A and between D. And then 6 meters on the top. So we're going to have 6 divided by cos 30 is equal to length AD, which is 6.9 meters. Right? So they're not overly calculated. It's just kind of keeping track of each of the parts and thinking about, well, ignore the other lines and think about just that one component. And if you know one side, this is symmetrical, so you know the other side. And then E says, what's the angle at the peak? I want to know what's the whole angle at the peak. If I know half the angle at the peak, I just double it. So we know it's 30 here, 90 is over here. So 180 minus 90 minus 30 equals 60 degrees. And then we have to double it, because this side is 60 and this side is 60. So the total angle at the peak is 120 degrees. And we have pretty well all of our angles that we would need in order to do calculations, in order to do our cuts. You could go through and you could fill in what the rest of the angles are just based on that information. So not overly difficult. Do watch the angle at your peak. You always have to split that in half in order to get your right angle. So, or you'll have to double it, double the angle you would find up here in order to get the full angle at the peak. So that's one of those little things to watch for, is taking your triangle, you divide it in half, double check that the angle at the peak. Whenever a question asks for that, there's a couple of questions on SAM that you do get the correct angle at the peak. Make sure you include both sides. All right. Well, this one's not too bad. When I printed the notes, it didn't print overly clear, so I had adjusted it a little bit. But I think we'll just leave them as they are, and I'll adjust my calculation a smidge to compensate. So we want to find out what angle each factor makes with horizontal and what is the angle at the peak. So the angle at the peak is going to be the full angle here. Now the first thing you'll want to do is probably convert your fractions into decimals. So this one, 4 feet is 48 inches, and 5/8 of an inch is 0.625. So that's 48.625 inches. This is going to be 144 inches, and this is 144 inches. And then we have 5 and 11/16. Will give you a height of 125.6875. Okay, so we've got lots of decimal numbers to bother with here. So let's make our right triangles. I'm going to cut this in half here. Okay, don't have the best drawing abilities. All right. So we have 2 triangles, and they're 2 different size triangles. They both have the same width, but this one has a different height. So we're going to have to think about the 2 triangles separately. So we'll just draw the triangle for this side, and we're going to figure out what's the angle at the base, and then I'm going to find, I'll call it angle 2, the angle at the peak as well. So we know we have 144 inches, And then here on this edge, it's going to be 125.6875 minus 48.625. Oops. I'm going to double check. I had a calculator error come up. And it gives me the same number, so it must have been behaving properly. Trying to use a stored number and it wasn't 100% sure. So 75.0625. If I want to know the angle at the bottom, I'm going to use tangent. Opposite over adjacent. So the tan of my angle is going to be 77.0625 divided by 144. And we get tan of our angle is equal to 0.5352. And then we do tan minus 1 of 0.5352. And you get 28 degrees. So we know this angle is 28 degrees. We have a right angle over here of 90. So what is this section of the angle at the top? It's going to be equal to 62 degrees. Now let's calculate the other side. Again, we have 144 inches. And we have a height this time of 125.6875. Obviously, I haven't drawn it to scale. I'm just trying to squeeze it in. And I want to know what happens to be the angle at the base here. So the angle at the base on this side is going to be tan opposite 125.6875 divided by 144. And you will get, if you rearrange that properly, you are going to get 41 degrees. Okay. So 41 degrees there, that means this side at the peak is going to be 180 minus 90 minus 41 is 49 degrees. So angles with horizontal. Angles with horizontal on the left, we have 28 degrees. On the right, we get 41 degrees, and the angle at the peak is going to be 62 degrees plus 49 degrees, leaves us with 111 degrees. I made a couple of calculation errors lately, and I've been having some students tease me about the calculation errors. So I'm trying to make sure I double check that I've done just a quick mental. All right, so again, it's not too complicated when you're doing things like rafters. The hardest part of this one, you had to convert to decimals, and then you had two different peaks. So we had to look at the two roofs separately, but not overly complicated, pretty straightforward. Once you've done a little bit of the trig, you're pretty well on the right track. It's just finding that right triangle. The very last one looks complicated, but it is super easy. Okay, so you have a gazebo floor plan. It's 177 inches across. I want to know what is length X. Now it looks like there's not enough information because if you look at this, you say, well, where is the angle? But I think you know enough information to find the angle. If I start here and I go all the way around in a circle, how many degrees have I gone? You've gone 360, full circle. Well, how many triangle sections are there? There's one there, 2, 3, 4, 5, 6. You have 6 triangles. So 360 degrees divided into 6, because 6 triangles make up that 360 degrees, gives me 60 degrees. So up here, I have 60 degrees. Okay? Now I want to try to figure out how long x is. Do I know how long one of the sides are? Well, we definitely do, because this is 177 inches all the way across. So I know that if I go just to the center, it needs to be 177 divided by 2, which will give us 88.5. All right? Now, where's my right triangle? Well, here's my right triangle. I'm going to get rid of a little ink here, and we'll give you the right triangle. So our right triangle, we'll trace it here, is right there. We know that the whole triangle, so the non-right triangle is 60 degrees, so this one is 30 degrees. 88.5 was half of this distance, so that must be the length distance to the middle. And I will need to know, what's this length? So let's look. 88.5 is equal to hypotenuse. This side is our opposite side, so we must use sine. So sine of 30 is equal to opposite, which I'm looking for, over the hypotenuse, which is 88.5. Rearranging that, we will get the opposite is equal to 88.5 times the sine of 30, which, plugging into your calculator, you will get 44.25. So x is double this distance, so x is equal to 88.5 as well. So 2 times 44.25. Now, let's just stop for a second. Is there a way we could have predicted that the length of side x would be the same as the length of the hypotenuse, or the distance to the center? Now, sometimes we forget things that we've learned before, and this is, I'm not going to test you on this, but this is something for you to kind of refresh your memory. Equilateral triangles all have the same length of sides. And one thing about equilateral triangles is they all have 60-degree angles. So you'd have 60, 60, 60. And if one angle in a triangle is equal to 60 degrees, you're going to end up with the other angles equal to 60 degrees as well. So this is why the hexagon gazebo is easier to calculate, because you actually get equilateral sides. Right? So pretty easy calculation. Actually, at first it probably looks complicated, but hopefully by the time you finished it, you went, oh, that's not nearly as complicated as I thought it was. Right? So that finishes off this section. There's a couple questions in a quiz just to give you a little extra practice doing a couple rafter calculations. And then you're ready for your assessment, which I hope to have your other assessments marked back to you before you are ready to submit the assessment for this section. So that has us all finished.